Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So, we've taken a little bit of a break from our usual content with the linear algebra series recently. We've been looking at some different things, and today I want to continue with that theme of slightly different things, and I'm going to return to the Programming for Fun series that I used to do, or Adventures in Python, I think it's called, in the playlists on my channel. And as promised, I'm going to do a quick tutorial on how to make a visualization of the Lorenz Attractor in 3 dimensions using Blender. If you don't know, Blender is a free and open source 3D modeling software. It's totally amazing. The user interface takes a little bit of getting used to if you haven't used it before, but once you get the hang of it, it's very good. Now, I want to say just right up front, this is not intended to be a beginner's tutorial for Blender. If you've never used Blender before, then I suggest before trying to follow this tutorial, obviously download, acquire Blender, and then go and look at some of the excellent beginners tutorials there are out there for Blender that you can find on YouTube and wherever. I'm going to assume that the viewer, that you have a basic knowledge of using Blender already and really just going to cover the details of how to actually create the Lorenz Attractor visualization. I hope that will be of interest. Right, and just quickly to say, as I usually do, if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. I do try to make videos fairly regularly, so if you subscribe, you don't need to worry about missing anything. Thank you very much. Anyway, let's jump into Blender and have a look how we can create a visualization of the Lorenz Attractor. So here we go. When you fire up Blender, you will get something that looks like this. I'm using Blender version 2.92, which I believe is the most recent version at the time that I'm doing this. And so we will see this as the default view. The very first thing we're going to do is get rid of the default cube. We don't need that, so just select it and hit delete. And we don't really need to worry too much about anything that's going on, anything else that's going on in our scene. And one thing I just want to say, that for doing this kind of thing, it is better if you start Blender from the command line, because then you can get errors and things from Python scripts. I should say that we are going to be using Python scripting in Blender to actually create the Lorenz Attractor, and then having a quick look at how we're going to use the features in Blender to make it look nice. Okay, the first thing we want to do is we need a text editor. Now, conveniently, Blender has a Python interpreter and everything already in it, which is fantastic. All we need to do is drag from there to split the screen into 2, and then we're going to change this screen to be a text editor, and we'll get something that will look like this. And then we simply select new to create a new file, and into here we can now type our Python code. And so the very first thing we're going to do is type import bpy. And one thing I'm just going to do, I'm going to make this a bit bigger so you can see more clearly what I'm doing. Okay, so import bpy, that just brings in all the Blender functionality into Python that we're using, and we're going to create a class for the Lorenz Attractor, and we're going to compute the Lorenz Attractor. We will compute the attractor using the finite difference method. Okay, now that's important. If you remember back, if anyone watching this has been following my channel for a while, you'll remember that a while ago I made a video looking at the Lorenz Attractor using Python and Pygame. That's actually one of my more popular videos. I'll put a link up here somewhere so you can go and have a look at that. A link in the description below as well. And yeah, in that video we explored 2 different ways of computing the attractor. We did it using the finite difference method that I'm using here today, and then we also went on to look at using the ODE, ordinary differential equation solver, that we get from SciPy. Now, the trouble with using Python in Blender is that we have NumPy, which is great, so we can use all the functions of that, but we do not have SciPy. And I haven't figured out a good way to bring SciPy into Python that's incorporated in Blender. There may be a way to do it. I don't know what that is at the moment. So what I've done is simply limit myself to using the finite difference method. And since we're really doing this to produce a visualization, something that looks nice but is still the Lorenz Attractor, then we don't really need the precision necessarily that we would get from using a proper ODE solver. Okay. So that said, let's carry on with our code. And in fact, actually, if you look back at the previous video, you will see that the code is going to be more or less the same, at least that generates the attractor. So let's have a look at that. So the first thing we're going to do is create a class, which we're going to call, if I could spell, class Lorenz. And this is going to have a constructor, which is simply going to accept as input a reference to our scene. We want a name for the object that we're going to create. We want to be able to specify what color we want it, and then we want to be able to specify the initial x, y, and z coordinates. Okay, so those are going to be the coordinates, the starting point for the attractor. So the first thing we do is we need to store self.x, self.y, and self.z, which with the values, there we go, of init y, init x, init y, and init z. And then we need to define some of the parameters that we're going to be using. So we're going to use dt. This is our time step. So self.dt is 0.005. That's the value that I've used. You can use different values. You can experiment with those. Smaller values will give a more accurate solution to the differential equations, but obviously it will require many more points. And then we define the parameters for the attractor itself. We have self.a, self.b, and self.c. Those are normally defined as being 10, 28, and 8/3. Those are the standard values that give the classic butterfly shape attractor. You can experiment with those. We store the color, self.color equals color, that's easy. Self.object name equals object name, to store all of these properties so that we can access them from other functions. Self.sceneRef equals sceneRef. Okay, and that's everything we need for our constructor. So what we're going to do now is define a function called step, and the purpose of this is to step through the solutions to the differential equations. Now I've already written these out, and I'm going to copy and paste them so that I don't make a mistake. So here we have the first line. So we have self.x is equal to self.x plus the time step self.dt multiplied by a multiplied by self.y minus self.x. And if you refer back to the actual differential equations, well, I'll put them on the screen here so that you can see those. And if I tap in the right place, there we go. We have the same sort of thing for y, and we have the same sort of thing there for z. Okay, so that's our step function. So every time we call step, we're going to modify the values of x, y, and z that we're storing in our class to be equal to the previous values of x, y, and z, plus some other value that we're calculating based on the previous values of x, y, and z, and the parameters of a, b, and c, according to the equations that we've just seen that define the attractor. And that is the basis of the finite difference method for solving differential equations, or for approximating a solution. Anyway, and we then need a function that we can call that will allow us to actually generate the attractor. So we're going to call that generate. So we have define self, define generate, and in here we're going to define the number of points to use. Now we could pass that as a parameter, but I haven't done that, and we're going to use 10,000 points. Okay, now we're going to create a curve data block. So we're now doing specific Python stuff, and I really must say at this point, I am not an expert on using Python in Blender. I'm learning this as I go, and I had to do quite a lot of Googling to figure out this. And this piece of code that I'm doing now, and actually how to create the curve object, is very much inspired by a post that I saw on the Blender Stack Exchange. I'll put a link to that specific post in the description below. I hope it's okay that I haven't copied and pasted from that, but I was very much inspired by it, and so I really do want to credit the author of that post. So as I say, link in the description below to the original. And yes, what I've done is take that and then adapted it to suit my specific purposes. Okay, so what we do first is we create a curve data block. Data blocks are, I believe, the essential structure of the .blend file that Blender uses. So when you want to create anything, if it's a curve or a material or a mesh or whatever, you create a data block into which you put the data, and then you create the relevant object from that, as I understand it. Okay, not an expert. Okay, first thing we're going to do is we're going to create a curve data block, which I'm going to call self.curve, and we create it using bpy.data.curves self.new, and we're going to call it Lorenz curve. Makes sense, right? Because that's what we're working with. And it's going to be type equal curve, like that. Okay. And then we have self.curve.dimensions equals 3D. Okay, now actually you can understand quite a lot of how this works simply by looking at the normal Blender user interface. If you create a curve, if you do Shift A to add an object and you add a curve, and then you look at the curve properties, you can see it has these properties of dimensions and so on. So we're really just setting those properties from our Python code. Okay, and we have self.curve.bevel depth, because we obviously want it to have some thickness, and I've set that to 0.1. I found that that does work quite well. Okay, I'm now going to create a new, oops, if I could spell, a new spline poly, which will be linked to the curve data block we just created. Okay, come back, there we go. So we're going to call this Attractor poly. We don't need future reference to this, so we don't bother storing it in self. In fact, actually, I don't really need to store curve with self.curve either, but anyway, that's all right. So attractor.poly is equal to self.curve.splines.new, and we're going to create a new polyline. That's the type of curve that we want to create. And attractor poly.points.add, and then we have num points minus 1, because we have one less than the number of points that we've defined. So we define num points equals 10,000, so we have 9,999 points, and because of course it includes the 0th point. Okay, so that's that. And now what we're actually going to do now is generate the coordinates for the polyline. This is the actual interesting bit, really, that creates the attractor. We simply do for I in range, oops, if I could spell, for I in range 0 to num points, colon, okay, and attractor poly, oops, attractor poly dot points I dot co for the coordinates equals, and then self.x, self.y, and self.z, just like, oh, and we need a 1 at the end there because that accepts 4 dimensions. Okay, so we simply do that. So we're taking self.x, self.y, and self.z from our class, and we're simply going to store those into the attractor poly. And then, of course, we need to call self.step to compute the next values of x, y, and z. And you can see that's simply going to loop through, and each time through it's going to calculate the necessary values of x, y, and z. Okay, so that will actually create the points, that configures the polyline, but that won't actually put anything into our scene. What we need to do now, oops, here we go. What we need to do now is to create an actual object. Okay, we're going to call it self.body, because it's the body of our object, equals bpy.data.objects.new curve and self.curve. Okay, just that. And then that still won't actually do anything if we were to run that. So we need to rename our object and add it to scene. Okay, so we do self.body.name, oops, equals self.object_name, which we stored in the constructor, and then we do self.sceneRef, okay, that's the parameter that we had passed, .collection.objects, like so, .link, and self.body. Okay, and that's actually everything we need for the Lorenz class. That will create the Lorenz Attractor. It will create a polyline object and configure it the necessary points, and then actually link it to the scene collection so that we can actually see something. So let's just have a look at what code we need to put in now to actually make that work. Save that first. So the first thing we need to do is get a reference to the scene. Okay, so scene is equal to bpy.context.scene, right? And then we can actually create the Lorenz, of course it's a name, it should be a capital L, create the Lorenz Attractor. Okay, so just call this Attractor 1, because you could have as many as you want. equals Lorenz. We pass the reference to the scene. We can call it Attractor 1. And then we pass our color. So initial, the nice orange I like to use is 1, 0.40, and an alpha of 1 because we don't want it to be transparent. And then we pass the initial coordinates, 0.1, 0, and 0. And interesting to note, actually, I have bothered having color as a parameter, but you will note that we haven't used that anywhere. And that's something that I'll leave for the viewer. If you want to go on to add that yourself, you can. You could add code in there to actually set the material and the color and things. But I'll leave that as an exercise for the viewer. Okay. Okay, and finally, to actually generate it, we have attractor1 dot generate, just like that. And that is everything that we need. So well, now that we've created our actual code, all we need to do is hit the run button up here, this one, okay, and there we go. So we see over in the 3D view, let's just resize those and let's zoom out, and we see, there we have it, our beautiful Lorenz Attractor, wonderfully displayed in 3D. It's really rather fun actually, just to swish around and stuff, and you see it appears here in the scene collection. It's called Attractor 1, exactly as we specified. Now, one thing to note, if you run the script again, it will I'll just show you actually what happens. So let's just expand that again. If we run the script again, you see what happens. It simply creates another attractor. So you have to remember to delete the attractor you're working with, whatever. And yeah, so I'm going to change the bevel depth to 0.2. And let's run that, so we get something a little bit thicker, and you'll notice this looks a bit more like the display that I created before. Now obviously you can go through and you can set this up with lights and set up the camera and everything exactly the way you want. One thing I just want to do, because at the moment this doesn't look anything like what we had before. In fact, actually forget that. What I'm going to do, I want to show you how I set up the scene. The first one thing I did is I deleted the light, and we want to view something like that. So what I'm going to do is select the camera, and we can go to view, cameras, viewpoint to camera, no, align view, here we go, and align active camera to view. Okay, so that puts our camera, so if we switch to our camera view, now we see that. And then I quite like to use navigation and walk navigation, and actually then we can just use WAS and D standard keys that we can pull back. Now, one thing you'll notice actually, because the attractor is very large, our camera has to be really quite far away, and that actually makes things really quite awkward. So let's cancel walk navigation, select our attractor, press S to scale, and scale it down to 0.25. And now what we can do is simply move in a bit closer like that, and we can select the camera again and go back to view and align view active camera to view, and view navigation, walk navigation, and now you see WAS and D will now work a lot better because we don't have to be we don't have to be so far away, and we get to where we want, and then just click the left mouse button to fix that. And let's just zoom in. So that's our camera view. And if I switch to the top view, I just want to show how I like to create lights and things for these sorts of scenes. So if we do Shift and A, I'm going to add a mesh plane, and we can leave it with the default size. Just press G to move that over to here, and GY, let's put it over there, something like that. And now I want to rotate it, so it's sort of that sort of angle, and just move it up like that. Okay, so you see what we're doing. If we look at that in 3D, we're creating this plane there. It's still not the right angle. I want it to point that way, something like that, and we can scale it as well. Let's make it a bit bigger, something like that. Okay, so we have this plane, it's facing that way. And what we do now, what we're going to do is we're going to set our renderer, not EV, to renderer to cycles, and select the plane that we've just created, go to materials, click new, and instead of principled BSDF, we want to set this to be emission. There we go. Color 1, color white is fine, strength 1 is fine. So that should give us a light source. If we look at our camera, and let's just hit cycles and render, and you see we start to get something that's not particularly interesting yet. So let's just go back to the normal view, select this again, and we're going to duplicate that object and put the other one somewhere over here and rotate it so it's facing the right angle. Check that that is indeed the case. All different sides. Yep, I think so. So go back to our camera view and cycles, and there we go. We start to see our scene, and we can change the color of our emission material. No, we don't need to change the color. We can change the strength. If we put that up to 4, then we start to see something a bit more interesting. If we select the attractor, let's give that a material, new. Okay, we'll leave that as principal BSDF, change the color to some kind of nice orangey color, if you like, or whatever color you want. Some kind of nice orangey color. We'll start to see that starting to look cool. And then to get the kind of look that I had before, I did a metallic of 0.5. And you see, we're starting to get the kind of result that I had in my video. Okay, so really there we go. That's everything I wanted to cover. That is the very basics of how to create the Lorenz Attractor, or a visualization of the Lorenz Attractor in Blender. And I've gone over and covered a little bit about how I configure it and everything to make it work and to make it look nice. And this is the technique I used to create the animation that you saw at the beginning and that I posted in a separate video a couple of weeks ago. So like I said, I'm not an expert with using Python in Blender. It's something that I'm learning as I go, but I wanted to share this really because I think it's really quite interesting, and I have taken inspiration from Stack Exchange, the Blender Stack Exchange website. Link in the description below to the specific post from which I got that inspiration. But you know, I think we really all do that, and really that's how to learn. And I just wanted to put this out there because I hope you know, it may be useful and inspiring to some of you to go and have fun and, you know, just play around with it. I did mention, actually, you don't forget you can vary the parameters that we defined for A, B and C, and different settings of those will produce sort of different effects. But the 10, 28 and 8/3, the default values are probably the best. They give the classic butterfly shape, from which of course we get the expression about the butterfly effect. And yeah, there we go. Anyway, so I really hope you've enjoyed this video, and if you have, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel and hitting the bell icon for notifications so that you don't have to miss any future videos. Anyway, like I say, I hope you've enjoyed it. It's been a great deal of pleasure making it, and I really look forward to seeing you in the next video. Thank you very much for watching. Bye.